Hello, in this video we will talk about titration curves as related to acid and base titrations and redox titrations. Okay, so I'm not going to spend any time talking about what is a titration. It takes 2 seconds to look that up yourself. What I'm going to do is focus on common mistakes that students make when they consider titration curves. And we're not going to get into massive detail here. We'll keep it to an introductory and general chemistry level. So there's 3 common types of acid-base titration. The most common one, typically the one you see first, is between a strong acid and a strong base. So I have a plot here prefabricated to save a little bit of time. If we were to plot pH on the y-axis, so the power of hydronium ion on the y-axis, and then whatever is on the x-axis typically would be the chemical that goes in your burette. So let's say more often than not you'll have a volume of base added here. So you typically will have the base in the burette. Then your profile will look something like this. So we'll start off with a slope, then it will asymptote, and then it will reach a plateau like that. Okay, so let's mark some features on our graph. If you were to look at this initial slope here, and then look at the final slope here, so I'm just going to draw a tangent to these lines, and then we look at this distance between these 2 lines, take the central point between the initial 2 dashed lines. This will be the equivalence point. The equivalence point is when you have essentially equivalent amounts of acid and base. So you have 1-to-1 ratio of acid and base. Okay, so essentially the chemistry is finished at that point. Whether or not your titration is finished depends on your skill level, but the experiment is finished at that point. So typically, if you have an indicator, and this video won't really be about indicators, but let's say you have an indicator in your to acknowledge the equivalence point, because typically these acids and bases are colorless. So you need an externally applied indicator to trip a color change at the equivalence point. Typically you have to overshoot the equivalence point to trigger the indicator. So ideally that's what you want. You want the final volume. You already have the initial volume, VI, you want the final volume, VF, and typically you want the change in volume. So change in volume is the difference between the final and the initial volume. So typically that's the payoff for doing a titration. You want delta V. You do have to overshoot the equivalence point to access the tripping of the color change for the indicator. And you want to overshoot as little as you have to, but notice it does asymptote. So your risk of error is pretty small. You will get a hard time off any instructor if you do overshoot the equivalence point. And I don't encourage you to say anything about it being an asymptote, because that might make you come off like an asymptote. But I would keep in mind that the error is going to be pretty small, especially if delta V is large. But do shoot for the stars anyway and try not to go much beyond the equivalence point. Okay, so if you've got a strong acid and a strong base, obviously this is a neutralization. Let's have a look at the pH at the equivalence point. So I'm going to show you that the pH is 7 at the equivalence point. So why is that? Let's take a generic expression for the acid and base. Okay. So let's call the acid HA. Let's call the base B. That's going to give HB plus and A minus. So the acid is going to donate its proton to the base to form HB plus, because remember it's donating a proton, and then we're going to be left with A minus. So let's label this real quick. This would be our Brensted-Lowry acid. This is our Brensted-Lowry base. You can look at my other acid-base video for more of a discussion on the Brensted-Lowry definition. That's not what we're going to do here. We're just going to assume you've seen that, talk about titration. So Brensted-Lowry acid, Brensted-Lowry base, conjugate acid, conjugate base. Okay, we're interested in the conjugate base of our strong acid. So let's take this conjugate base. The conjugate base in the presence of water is going to regenerate it's not going to regenerate anything. Okay, we have a definition rather. The conjugate base of a strong acid is pH neutral, which means 7. That conjugate base won't react with water. You'll have no reaction. And that's a definition I would remember. So it's because there is no further reaction with the conjugate base that we have a pH 7 at the equivalence point. So we can put here because no reaction of conjugate base of strong acid. Okay, so if we don't know whether something's strong or weak, one thing we can do is titrate it. Titrate an unknown acid with a strong base, measure the pH at the equivalence point. If it's 7, you have evidence you have a strong acid. Okay, so let's label that as 7. All right. So that's what I'd like you to know. That's what I'd like my students to know about titration curve for a strong acid and a strong base. What about a weak acid and a strong base? All right, let's go plot. Let's try and keep consistent with our color scheme. That's clearly the most important thing. pH here and volume of base. We'd start off for a slightly higher pH, and there'd be a hump, and then an asymptote. So there's 1, 2, 3, there's 4 slopes here. Let's go to the equivalence point initially again. So let's take the midpoint here. That's our equivalence point. Now the equivalence point is at a pH for this system. If it's a weak acid and a strong base, it's going to be greater than 7. It's nothing to do with the fact that you have a strong base. Don't think that the strong base just dominates the weak acid and that's why it's a basic pH. Let's look at the real reason why that's the mistake I'm trying to correct in this video. So let's look at why. Let's try and slot it in here. Hopefully that's enough space to do it in. So we have our HA plus B. Notice I'm going to put reversible arrows here. I didn't put reversible arrows here because everything was strong. But this is a two-way street. I'm not going to talk about equilibrium in this video either. I'm sorry. That would be another video. But I'm just going to say this is not a one-way street, and that's all I'll say. So we have B, H plus, and A minus. So again, here is our Brensted-Lowry acid, our Brensted-Lowry base, our conjugate acid, our conjugate base. Once again, we're going to be interested in our conjugate base. By definition, the conjugate base of a weak acid is basic. And that means pH greater than 7. And this is how. So let's see how, and I'd remember that definition. This is how it happens. You have A minus in the presence of water. It's going to produce the original weak acid. And by deprotonating water, it's going to release hydroxide ions. And this is what gives you the pH greater than 7 at the equivalence point. It's the in situ generation of hydroxide ions. Okay, so notice it's not the strong base that you add, it's the strong base that's produced during the reaction. So we have here pH greater than 7 at equivalence point due to in situ generation of OH minus ions. So it's going to be greater than 7. Okay, that's what I want you to know here. Notice there's I don't think we'll bother with this. It's a feature I'll mention, but we're not going to look at any chemistry of it in this video. In this region here, we have buffer formation. So I'll mention it only. You typically study buffers more in a second sequence of a general chemistry class, at least in any reasonable detail, which this video is not that video. But notice that the slope decreases, it flattens out, and that's because the buffer that you've formed is trying to resist further pH change. Eventually we overwhelm the buffer, but that hump feature and the pH at the equivalence point greater than 7 are telltale signs that you have a weak acid instead of a strong acid. Notice there is no such buffer feature with a strong acid. Okay. Thirdly, let's look at a strong acid and a weak base. Now, typically you want a strong system in the burette, so in this occasion we would probably have the acid in the burette and we'd add that to our base, which in this case would be in the Erlenmeyer. So let's label this appropriately. We're going to look at pH against volume of acid this time. Again, we typically want the strong system on the x-axis. So initially, when I've added no acid, I've just got a weak base. So I'm going to be down here. Ooh, choose the right color. So it's essentially going to be something like this. Let's look at our equivalence point again. Notice we have buffer formation again. So it's essentially an upside and rotated version of this graph, right? So if you flip this 180 degrees in the y-axis and the x-axis together, no, actually, if you just flip this 180 degrees in the y-axis, yeah, you'll get this. So with a bit of imagination, you can see that. Okay. What else do I want to say here? So we have this buffer region, we have the equivalence point. In this occasion, the equivalence point is going to be less than 7. So why is the pH at the equivalence point less than 7? Let's have a look. Okay, so we have, let's see, what would be the best way to explain this? We have a base. Let's see, what would be the best way to explain this? Trying to be consistent with the way I've explained this one. Yeah, it would essentially be the same. There's no point trying to draw it differently. I'll just recreate that again. So we'd have pH plus and A minus. On this occasion, though, I want to look, well, let's label it. I want to look at the conjugate acid. So we have the Brensted-Lowry acid, the Brensted-Lowry base, the conjugate acid, the conjugate base. But I'm interested on this occasion in the conjugate acid. The conjugate acid of a weak base is acidic, which means pH less than 7. So let's see why. We take the conjugate acid, which is pH plus, we add that to water because it's in the presence of water. Reversible arrows. We will protonate water to generate hydronium ion, and we'll regenerate our original base. And it's this hydronium ion which is acidic and gives us our pH less than 7. So we generate in situ hydronium ion. So the pH is less than 7 at the equivalence point because of in situ formation of hydronium ion. Okay, so that is why you would get a pH point at the equivalence point less than 7. Okay, weak acid, weak base, we tend not to do. So typically not used, since the equivalence point would be less easily measured. So we typically always want to have something strong in our titration, and for that reason, either both strong acid, strong base, which was our first example, or we have, so either that one as our first example, or this one where we had a strong base, this one where we had a strong acid, but we don't want everything weak. Okay, now a couple of typical calculations, and I'll be providing sample calculations with full workings and solutions to my students. But here's an example just for the video as well. So a sample acid-base titration calculation. The question reads, what volume in a milliliter of a 0.3428 molarity HCl solution is required to completely neutralize 23.55 ml of a 0.2350 molarity barium hydroxide solution. Okay, so that is our question. First thing we'll want to do is write a balanced chemical equation. So I'll shift to red here. Let's write a balanced chemical equation. Sometimes these can be provided, sometimes they won't. But you should definitely be able to produce your own equation. You know, similar to camping, don't go camping if you can't catch your own food. That's my camping advice for the video. Okay, so barium hydroxide, 2 lots of HCl to give barium chloride and 2 lots of water. So neutralization, base, acid, salt, water. Okay, we are going to have to do a dimensional analysis type question, type solution. So let's gear up for our dimensional analysis. Probably don't want to go that close to the margin. Let's try and squish it on here. Okay, and I know I want mil of HCl solution. All right, so I know I need to write mil of HCl solution here, and I know I quickly need to get it into liter because of the equivalence between moles and liter in molarity. So let's do that. I know 1,000 mil of HCl solution is 1 liter of HCl solution. So I can write liter of HCl solution here. I know from the question that 1 liter of HCl solution is 0.3428 moles of HCl. That's what molarity means. Molarity means moles per liter. So I have my equivalence now. I can now write mole of HCl. I know from the balanced equation that there are 2 moles of HCl equal to 1 mole of barium hydroxide. 1 mole of barium hydroxide. So I can write mole barium hydroxide. I know from the equation that I have 0.2350 moles of barium hydroxide in a liter. 0.2350 mole is equal to 1 liter of barium hydroxide solution. But I don't have a full liter of barium hydroxide solution. I have, let's see, how much do I have? I have 0.02355 liter. Okay. Remembering to divide any milliliters by 1,000 to get back into liter. I multiply all the numbers on the top, divide by all of the numbers on the bottom. I get 32.28, couple of non-significant digits now, 85. So I'm going to round this to 4 sig figs because my input is 4 sig figs. So I have my 4 sig figs and then I see what else my calculator gives. That first non-significant 8 adds 1 to the last significant 8. So my final answer is 32.29. 32.29 mil of HCl solution. So that's a typical acid-base titration calculation. So you've got a mixture of the quantitative calculations that you need and the qualitative understanding of what on earth is going on in the lab when you do this reaction. You need both, and a problem with the topic means a problem with one of these aspects. Okay, more examples for my students. For now though, let's move on to a sample redox calculation. So here's a calculation already prepared for us. What mass in grams of copper is produced from the reaction of copper 2 ions with iron solid to produce 25 liter of a 0.002 molar iron 2 solution? We're given an equation, so that's great. We inspect the equation, it's already balanced. We have one copper on both sides of the equation, we have one iron on both sides of the equation, and we have +2 charges on both sides of the equation. This is nice that they've given us that I've given you a balanced equation, because to balance redox equations, that's a whole other video which I have, and I think I've called it balancing redox equations. But that's a separate skill that definitely you should learn separate from doing these calculations, because that's definitely something you have to get used to. Mercifully, this is already balanced though. Okay, so we are going to set up our dimensional analysis approach to the solution. Sorry, I wrote that in an angle. Okay, so we want gram of copper, so we should probably write gram of copper here. We have our periodic table. I know the atomic mass is 63.55 gram. And we set that equal to a mole of copper. I know from the balanced chemical equation that 1 mole of copper is equal to 1 mole of iron 2+ solution. So I've got mole of iron 2+ solution. From the question, I know the concentration is 0.00200 mole, and that's molarity, sorry, so that's in 1 liter of iron 2+ solution. So I can put liter of iron 2+ solution here. But I didn't use a whole liter, I only used, well, sorry, I didn't just use 1 liter, I used 25 liters. So multiply everything on the top, divide by everything on the bottom. We're going to round this to 3 sig figs because of our mole concentration of iron 2 is only 3 sig figs. So our calculator says 3.17, so let's give an extra couple of digits, 75. That first non-significant digit adds 1 to my last significant digit, so it's 3.18 as our final answer. So there you have it. We have qualitative introduction to titration curves, and then finally a quantitative example of an acid-base titration calculation and a quantitative example of a redox titration. And that will conclude this video.